But the two topics we have to do today are sigma and pi bonds, and then hybrid orbitals. In both instances, there's no explanation required. It is just identification. So if we were to draw out the Lewis structure for something, could we then identify how many sigma and pi bonds are in that structure? What is the hybridization? Kind of like what is the shape or what is the bond angle? So a fair amount of this part of the unit dealing with bonding does require you to kind of memorize some things, memorize shapes, memorize angles. Same thing can be said with sigma and pi bonds that we're going to go over today. And as I say in the title slide, remember, yes, we draw lines for Lewis dot, but what's actually happening is electron orbitals are overlapping. Where that overlap occurs is what sigma and pi bonds are trying to define. So again, I'm going to right away go over to our animation here, and we're going to watch the animation of sigma pi bonds, and I might kind of talk over it as we are going here.
Ethane, ethylene, and acetylene. Click on one of the molecules to view an animation of the bonding in that molecule. First, consider the Lewis structure of ethane. Counting the number of VSEPR pairs of electrons around carbon 1, we find 4 VSEPR pairs. We should also count 4 VSEPR pairs around carbon 2. The VSEPR model predicts that the geometry about each carbon atom is tetrahedral. In valence bond theory, 4 sp3 hybrid orbitals have a tetrahedral arrangement. We can begin to explain the bonding in ethane if we assume each carbon atom is sp3 hybridized. Each hybrid orbital will contain 1 valence electron, accounting for the 4 valence electrons of each carbon atom.
Okay, so first off, tetrahedral, hopefully a reminder that you remember that shape. It has 4 things coming off of it. Now, it already is referencing hybrid orbitals that I'm going to show you second. Again, they can be kind of taught in either order. We're going to go over sigma and pi first, and then that'll hopefully make more sense when it comes to the hybrid orbitals. So when they mention things like sp3 in this one, or in the next one I show you sp2, you can kind of keep that in the back of your head for a little bit, and we're going to come back to that topic in about 10 minutes or so. But again, the focus of sigma and pi bonds are where the orbitals overlap.
The bond formed between the 2 carbon atoms is called a sigma bond. A sigma bond is a covalent bond formed by orbitals overlapping end to end. The electron density is concentrated between the nuclei of the bonding atoms. In this sigma bond, 2 electrons are shared between the carbon nuclei.
Again, a sigma bond is going to be directly in between the nuclei. Now, unfortunately, in this first example, it's all sigma bonds, so we're not really going to go into a pi bond yet until I do the next example. But the first bond between the 2 nuclei should make sense. Again, that's where the attraction is between nucleus and electron from its own and its neighbor's electron. Again, you add the hydrogens, it's going to say the exact same thing.
The remaining 3 sp3 hybrid orbitals on each carbon form sigma bonds by overlapping with hydrogen 1s orbitals. 2 electrons are shared in each sigma bond. A single bond is composed of 1 sigma bond. Lastly, rotation can occur about a single bond because rotation will not break the carbon-carbon bond.
2 things to mention about what they talked about. First off, sigma is single. So anytime you draw a single bond, that's a sigma bond. The first bond between 2 atoms is always a single bond. Even when I told you guys to draw out Lewis dots for things as you're starting to figure it out, first by making 1 connection. Well, that first connection is always the bond between the nuclei, which is called a sigma bond. Now, again, are you going to be asked to define a sigma bond? No. But for identification purposes, again, this C2H6 had 1, 2, 3, 4, 5, 6, 7 sigma bonds that made it up. Second thing they mentioned at the end was this idea of rotation. I don't know if that's going to be too much of a concern for you or not. Uh, when it comes to drawing a molecule more than one way, simply moving, like replacing this hydrogen on the top with a chlorine, moving that from the top to the bottom, doesn't mean you actually drew anything different, because as they said, rotation can occur on that. We are going to go to something with a double bond now, ethylene. In ethylene now, you are going to see examples of both sigma and pi bonds.
First, consider the Lewis structure of ethylene. Counting the number of VSEPR pairs of electrons around carbon 1, we find 3 VSEPR pairs. Recall that double and triple bonds are counted as single bonds in the VSEPR model. You should also count 3 VSEPR pairs around carbon 2.
Even notice how they just identify carbon 1 versus carbon 2. A very common thing on a test could be, tell me the shape based on carbon 1. Okay, tell me the hybridization, which again we'll go over in a little bit, based upon carbon 2. So that type of numbering system sometimes is useful on assessments.
The VSEPR model predicts that the geometry about each carbon atom is trigonal planar. In valence bond theory, 3 sp2 hybrid orbitals have a trigonal planar arrangement. We can begin to explain the bonding in ethylene if we assume each carbon atom is sp2 hybridized. Each hybrid orbital will contain 1 valence electron, meaning that for each carbon, we have accounted for 3 of its 4 valence electrons. The bond formed between the 2 carbon atoms is called a sigma bond. A sigma bond is a covalent bond formed by orbitals overlapping end to end. The electron density is concentrated between the nuclei of the bonding atoms. In this sigma bond, 2 electrons are shared between the carbon nuclei.
So recall on the Lewis dot that it's a double bond that's supposed to be between these 2 carbons. Well, here is the first bond, the sigma bond. So they're only representing one of it. Now it's going to ask us to put in the hydrogens first, and that's going to single bond. But then what we're eventually going to get to is carbon needs a second bond to get to that octet to use up all of its electrons. That second bond is not going to be directly between the 2 carbon atoms because there's already an electron cloud here. So that overlap has to occur somewhere other than directly between the nuclei. And that's when we start to enter a pi bond. Now again, first we're going to single bond to hydrogens.
When we add the hydrogens, the remaining 2 sp2 hybrid orbitals on each carbon form sigma bonds by overlapping the hydrogen 1s orbitals. 2 electrons are shared in each sigma bond. There is still one more bond to explain. Which orbitals overlap to form the second bond of the carbon-carbon double bond? Recall that when sp2 hybrids are formed, a pz orbital does not mix to form the hybrids. Each carbon atom has a 2pz orbital, perpendicular to the sp2 hybrids, that contains the 4th valence electron.
I don't know if I've ever written on this with this before. No, it's not going to work. All right, I'll show you what they mean by the 2pz. Actually, I can do it right now. Remember, you do 2p, and you'd have 3 things. Sometimes they call this the 2px, the 2py, and the 2pz. So, not really something you have to be aware of. They're just giving you a little bit more information that perhaps you need at the moment. But at the same time, what they're saying is that we need one more overlap to occur. Now, these p orbitals that are going to overlap can overlap on the top or on the bottom. So they can't overlap right in between the 2 because there's already an electron density there. That is what a pi bond is. A pi bond is when the electrons overlap somewhere other than in between the 2 nuclei. So in other words, when you create a double bond, one of those 2 bonds from the double bond is a sigma bond. The second one is a pi bond. That's the thing that we need to get out of this. So if I click on next, it'll show that overlap.
The pz orbitals can overlap in a side-to-side fashion. This type of covalent bond is called a pi bond. The electron density is concentrated above and below the plane of the nuclei of the bonding atoms. In a pi bond, Electrons are shared. In other words, the two electrons are free to move through both regions of the bond. A double bond is composed of one sigma bond and one pi bond. Lastly, rotation does not occur about a double bond. For rotation to occur along the carbon-carbon bond, the pi bond would have to be broken.
Again, that second to last statement, a double bond is one sigma and one pi. That's what you need to know. You are going to be asked just to identify how many sigma bonds are in this molecule, how many pi bonds are in this molecule. We're going to end with acetylene, which has a triple bond in it, so they're going to show you that relating to sigma and pi, although again, sigma is the first bond every time.
First, consider the Lewis structure of acetylene. Counting the number of VSEPR pairs of electrons around carbon 1, we find two VSEPR pairs. Recall that double and triple bonds are counted as single bonds in the VSEPR model. You should also count two VSEPR pairs around carbon 2. The VSEPR model predicts that the geometry about each carbon atom is linear. In valence bond theory, two sp hybrid orbitals have a linear arrangement. We can begin to explain the bonding in acetylene if we assume each carbon atom is sp hybridized. Each hybrid orbital will contain one electron, meaning that for each carbon, we have accounted for two of its four valence electrons. The bond formed between the two carbon atoms is called a sigma bond.
Okay, so we form a sigma
When
bond.
we add the hydrogens, the remaining sp hybrid orbital on each
Form a
carbon
sigma bond with
forms a
hydrogen.
sigma
I'm going to
bond.
skip ahead again.
There are still two more bonds to explain. Which orbitals overlap to form the second and third bonds of the carbon-carbon triple bond? Recall that when sp hybrids are formed, a py and a pz orbital do not mix to form the hybrids. Each carbon atom has both a 2py and a 2pz orbital that can overlap. Each p orbital contains one valence electron, accounting for the third and fourth valence electrons for each carbon atom. Both the 2py orbitals and the 2pz orbitals can overlap in a side-to-side fashion. This type of covalent bond is called a pi bond. The electron density is concentrated above and below the plane of the nuclei of the bonding atoms. In each of the pi bonds, two electrons are shared. In other words, the electrons are free to move through both regions of the bond. A triple bond is composed of one sigma and two pi bonds. For rotation to
That's what
occur
you need
along
to
the
know again.
carbon-carbon bond, the
It's
pi bond
counting
would
that
have to
we're
be
doing
broken.
today. I'm teaching you how to count stuff. And what I like about these animations is it starts off right away relating it back to shape. Because one of the things I'm going to have you guys do here in a little bit, the grid sheet you picked up on the way in, is going to have you relate shape, bond angle, hybridization, and sigma and pi bonds all together. There's just a lot of different ways to explain bonding for the similar thing. So again, here's what we should have picked up from that example. The first bond is always a sigma bond. The second and third are both pi bonds. I'm going to give you an example right now of 1,2-dichlorine ethene. If I were to ask you how many sigma bonds are in this molecule, I would count 1, 2, and it doesn't matter if I pick the top or the bottom here, 3, 4, 5. So there's 5 sigma bonds. How many pi bonds? That double bond is the one. That's sigma pi bonds. Again, it's more complicated to explain where the overlapping is occurring and all that. That is not the goal in AP chemistry. The goal that you have to accomplish is being able to count them out. One last thing I want to bring up, and why I picked this particular molecule, is this relates back to what we did last class. I believe on the last page of the POGO packet, it gave you different versions of something like this. So for example, it could have gave you another drawing that was like this. Again, same elements, different structure. These two are considered isomers of one another. One of them is polar covalent, one of them is non-polar covalent. Okay, even though they have the exact same bonds, last class, and why I brought up this example so I can remind you of last class, the idea of not just bond polarity, because there's definite bonds that are polar here, but molecular polarity was brought up. Which one's polar, top or bottom? Top, right? Remember that there's a dipole moment there and there. Carbon-hydrogen bonds are pretty close to being nonpolar completely, so we're going to call them nonpolar. If I do that in the bottom one, the dipoles on the bottom one are the exact strength and opposite direction. They cancel each other out. This is a nonpolar molecule on the bottom. The top, however, has a net dipole that's going more in the upward direction, so that one is polar instead. So I wanted to bring that example up to you, and if you looked on my note sheet, what I wanted to do is pause for a minute and have you draw out these two molecules and figure out how many sigma and pi bonds there are. Now, naming-wise, again, we're not all as strong, equally strength, so I'll help out with the formulas. Hydrogen cyanide's HCN. Nitrous acid is HNO2. And what I would mention about an acid, it is very common when you have a polyatomic ion, this is the nitrite polyatomic ion, that hydrogen is bonded to one of the oxygens. Because in an acid, usually the hydrogen that's lost is bonded to the oxygen. So take a minute or two to draw those out and identify it, and then we'll go over those. And then we move on with hybridization, which hybridization is another kind of drawed out, counted type thing. In the first one, hopefully you recognize that there is 2 sigma bonds. And there's also 2 pi bonds. Remember, a triple bond is composed of 1 sigma and 2 pi. The second one doesn't matter how you kind of draw it out, and quite frankly, how I draw it out isn't a good representation of its shape. Because in the nitrogen, it has 3 domains coming off of it, should be a little bit bent. Well, that's kind of okay, I suppose, but that oxygen should be bent as well, and I have it drawn more linear. So again, I wouldn't take off if you drew it that way. However, you should then recognize what is the shape coming off the oxygen, for example. Again, here I count 3 sigma bonds and 1 pi bond. So this is half of what we needed to go over today, which is just another application of Lewis dot, another way to explain how bonding occurs. We all right? Okay. Hybridization. So let's go back to the animation to look at that. And then, as I said, we're just going to treat this like counting.
In the 1930s, Linus Pauling introduced the concept of hybridization to explain chemical bond formation. Hybridization is the mixing of atomic orbitals in an atom to generate a set of new atomic orbitals called hybrid orbitals. Click on one of the hybrid orbital buttons to see how hybrid orbitals are produced.
Okay, we'll start with sp3 because that's what we started with the sigma pi bonds.
Mixing an s orbital with the 3 p orbitals generates 4 equivalent sp3 hybrid orbitals. Note that the number of hybrid orbitals produced is equal to the number of atomic orbitals that are hybridized. The set of 4 sp3 hybrid orbitals has a tetrahedral arrangement. The angles between the orbitals are 109.5 degrees.
Typically, Knowing sp3 is tetrahedral is good. However, one of these orbitals could be an unbonded pair. And if that were the case, it actually wouldn't be 109.5 because it would be more of a trigonal pyramidal shape. If you see 4 domains, that's sp3. Think about it, sp3. Add up the s and the 3 p's, you have the number 4. You see 4 domains, whether that is bonded or unbonded. Either way, that is going to give you that sp3 hybridization. Similar thing can be said if we look at sp2.
Mixing an s orbital with 2 of the p orbitals generates 3 equivalent sp2 hybrid orbitals. Note that the number of hybrid orbitals produced is equal to the number of atomic orbitals that are hybridized. The set of 3 sp2 hybrid orbitals has a trigonal planar arrangement. The angles between the orbitals are 120 degrees.
If it were 3 bonds coming off, and again it could be single, double, whatever, then it would be trigonal planar at 120 degrees. Recall, if one of these domains was an unbonded pair, that would change this shape and that angle. But in sp2, you have sp2, if you see 3 domains total, that's sp2 hybridized. And finally, sp.
Mixing an s orbital with one of the p orbitals generates 2 equivalent sp hybrid orbitals. Note that the number of hybrid orbitals is equal to the number of atomic orbitals that are hybridized. The set of 2 sp hybrid orbitals has a linear arrangement. The angle between the orbitals is 180 degrees.
Now this one there's no way around, because I can't replace one of these with an unbonded pair, because then it's not actually bonded to another thing. It's not really in the middle of anything. So sp, 1s, 1p, you have 2 electron domains. So you are going to be linear, you are going to be 180 degrees. And if I go back to my last slide here, again, if you treat it like counting, there's 1s, 3 p's, you see 4 domains, it's sp3 hybridized. That doesn't matter if it's 4 bonded pairs, if it's 3 bonded pairs and 1 unbonded pair, if it's 2 bonded pairs and 2 unbonded pairs. 4 domains is sp3 hybridized. Just like sp2, 1s, 2 p's, there's 3 domains. Once you kind of either jot that down or think about that, I'd like you to go back to the drawings that we just did. And then you're going to identify the hybridization on those central atoms. Just like we can identify shape on central atoms, we can identify hybridization on central atoms. Because if I go back to our goal for the day, it even talks about ideal bond angles, sp hybridized, sp2, sp3. So this idea of hybridization is something they want you to be aware of. So look back at these. And in the HCN, there should just be one answer because the carbon is the one central atom. But in HNO2, there's 2 different central atoms, the nitrogen and the oxygen. So take a few seconds here to think about what would we call the hybridization for each of those central atoms. If I recognize HCN is linear, that means 2 domains, it must be sp hybridized. In the HNO2, the nitrogen has 3 domains coming off of it. The double bond, the single bond, and the unbonded pair. Because it has 3 domains, it is sp2 hybridized. Again, think of the S as a superscript of 1, so you're adding the superscripts. There's 1 S, 2 Ps, that's 3 total orbitals. You could ignore the animation talking about how it's 3 sp2 hybridized orbitals or 2 sp hybridized orbitals. You don't need to know that. You need to know identification. Just like in the oxygen, there are 4 domains, because again, that oxygen isn't actually linear. It's a bent configuration with 4 domains. That is sp3 hybridized. I truly think if you can think about how to draw a Lewis dot and then the different ways to identify that Lewis dot, which is either the shape, which we started off last week early on with, and bond angle, and now we're getting into hybridization and how many sigma and pi bonds. If you can connect all those, hopefully that will help you then in truly understanding how bonding works and how you're going to be assessed on the test next time.